Hi, so in this video we are going to learn about the relative stability of carbocations. What we're going to see is that carbocations can be stabilized by neighboring alkyl groups. So again, what are alkyl groups? They are methyl, ethyl, propyl, butyl, etc. Just simple alkyl chains, it's alkyl substituents. And so these groups, they stabilize neighboring carbocations next door through a special type of orbital overlap, which is called hyperconjugation. Why is it called hyperconjugation? Let's draw some pictures of this orbital overlap. First of all, let's recall the structure of a carbocation. Here I drew a methyl substituted carbocation, and remember the hybridization on the positively charged carbon atom is it's sp2, right, with an empty p orbital. I'm showing here. Now the methyl group, which is next door to the carbocation, that's the one which is stabilizing the carbocation. And to see why, let's draw a picture of the carbocation again. This time we draw out the methyl group, and you see I'm showing you this empty p orbital on the carbocation, which is important. Now you have to realize that just next door to the carbocation we have an orbital which is filled, and which is nicely aligned with the p orbital, as you can see, and this is the filled sigma orbital of the CH sigma bond. Okay, I highlighted it here in green. Now as you can see, there is actually nice orbital overlap between this empty sigma orbital and between the filled sigma orbital and the empty p orbital of the carbocation. And so that provides stabilizing orbital overlap, sigma to p orbital overlap. So we will really see that the methyl group stabilizes the carbocation by donating electron density into the empty p orbital. So now this hyperconjugation explains the following trend in carbocation stability. Essentially what we'll see is the more alkyl substituents we have on a carbocation, the more stable the carbocation becomes. So here we'll be drawing a couple of carbocations, and the stability is increasing towards the right. Okay? So the least stable carbocation is a methyl carbocation. This has no alkyl substituents, right, which can really align with the empty p orbital. That's the least stable. The next stable will be a primary carbocation, which has one alkyl substituent. And this is then followed in increasing stability by a secondary carbocation with two alkyl substituents. And finally, we have a tertiary carbocation, which has three alkyl substituents. That's the most stable. So this is the trend in cation stability. So increasing the number of alkyl substituents increases the stability of a carbocation. That's what I want you to remember. And this is due to the increasing number of sigma bonds, which are really aligned with the empty p orbital. They can stabilize the carbocation by donating electron density into there. Thank you for watching.